Paris. And after some application that he did as application of this theory of sheaves, which is at the back of most of algebraic topology and topology nowadays, he went back to more subjects inspired by real world progress. So I wanted to tell this story because it's really an amazing story that we will have more documents about it. And now I show you on this photo after the war. It's the Congress, it's the International Congress, thank you, in Nice. I don't know if you see well. In the back, in the left is Le Ray. The man you see from the back is Henri Kantor, one of the fathers of Bourbaki school. And on the right is Sobolev. So these three men have also from the point of view of pure and applied mathematics strong stories to tell, because Le Ray, I started to tell you how he switched from pure to applied and backwards. And Sobolev is essentially the creator of part of modern functional analysis. He's in fact the creator of generalized functions, but he stopped his mathematical life for a while because he was the scientific chief of the first Russian atomic bomb. He disappeared from university and even family life for many months to direct the scientific aspect of the Russian bomb. I don't know which name of the bomb it is. And Kantor was the creator of Bourbaki. Okay. So this is one part I wanted to tell. Another part I want to tell, maybe you show me, I don't know what is the next one. I don't remember. Oh, that's a different one. So maybe we go back. Thank you, sorry. I will say a few words about hydrodynamics and Arnold, because I was here for this congress in homage of Arnold. And of course, in Russia, the failed division I was mentioning between pure and applied mathematics has taken very different aspect due to sociological, political, cultural reason that I don't have time to develop, but I'm sure that one can say some things about the differences in Russia, the specific characters. And as you know, Arnold did a lot of work connected with physical problems, and in particular, he had some famous results in hydrodynamics and in dynamical systems. And in particular, there's a famous result that was shared by three authors, although the real first author, as everybody agrees, is Kolmogorov. Kolmogorov, Arnold Moser theory, CAM theory. The story of CAM has been told many times. One thing interesting is that Kolmogorov, when he had these results, was coming to France to give a talk about these famous results, and he saw, before coming, he saw that there was an approach to the same result in the book of two applied probabilists in France, Fortet, Blanc-Lapierre and Fortet. And when he came to Paris, another strange event, somebody asked him whom he wanted to meet, and he said he wanted to meet Kolmogorov, whom I'm going to show you. He wanted to see Grothendieck, who is the famous mathematician, one of the most important mathematicians of 20th century, at least from our point of view, and Fortet was an applied probabilist that nobody really knew in the milieu of French pure mathematicians. And Kolmogorov was supposed to give 2 series of lectures, and the second series was about his KAM theory, which is a very deep, important result, but has many applications also. And at that time, it was 1958, and there was a menace because the Algerian crisis was at its top, and there was a menace that the French soldier officers would come from Algeria and take power in Paris, so the Russian embassy ordered Kolmogorov to go back. So that the French had to wait to learn the details about the theory, for which they had specialists, applied mathematicians that could explain this theory. Many testimonies show various connections between mathematicians, physicists, theoretical physicists, and experimental ones, and very closer in Russia than, for example, in France. When I asked Yasha Sinai, who is a mathematician, Russian mathematician now in the States for many years, about pure and applied mathematics, he sent me a copy of an article of his. I want to give you the exact title: Mathematician and Physicist, 2 points, Cats and Dogs, interrogation, comma. So he wanted to, with an interrogation mark, so of course he wanted to say that they mix together, but sometimes it's with some difficulties. Of course, he was restricting to physics. I was not thinking specially of mathematics and physics. I was thinking of application in general. But just to conclude about the Russian part of my expose, I think that one of the deep reasons of this closer connection between pure and applied parts of mathematics in Russia has to do with political organization of the state. For example, I know I have quite a few good Russian mathematician friends, good friends and good mathematicians who have spent a lot of years in institutes which were applied, and they were doing pure mathematics, but sometimes in connection, like the Institute of Передачи Transmission of Communication. It's really a structure we don't have the same in France. And that's one reason. And the second reason is also cultural reason. There is a strong tradition of what is called in our country, in the West, it's called holistism, or holistic view, that goes back to Lomonosov, and I think that's also one element. So now I want to say a few words. I don't know how long you can support me, but I want to say a few words about the philosophical issues. Hidden behind the distinction between mathematics per se and mathematics operating in the world, there is a deep philosophical question: the applicability of mathematics. How is it possible that purely mental activity, playing with ideas, numbers and symbols, construction in the Platonic realm of ideas, can act on our world, help us to predict tides, make rockets hit their targets, and announce the results of future elections? The question was already asked by many people, so I could quote Kant, and I quoted this proverb at the beginning of my talk, but this proverb was also not quoted, but used by famous article in the years 1940s, Flexner, The Usefulness of Useless Knowledge, and Wigner, also the scientist, wrote an article called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. This is in 1960. Partial answers have been given to this question of applicability, in particular a recent book by Steiner, or I've seen recently some article by a philosopher, I think he's a philosopher, but I don't know where, Vladislav Shaposhnikov.
Mm-hmm. From Moscow State University.
Moscow State, yes.
Mm-hmm.
And recently, an original method, I will make two remarks. recently an original method has been sketched by Mikhail Gromov, mathematician, who is also working on biology. And this article, which I will simply quote here, he has various articles, but one is called Great Circle of Mysteries, Mathematics, the World, the Mind. So you can find, I can give the website address, but I think his book has been published, there's a book that by him that has been published recently in Moscow in Russian with the same title, Mathematics, the World, the Mind. So probably he has reunited some articles. It is a strange mixture of development inspired by a Spinozan view of the mind-body problem and recent developments from cognitive sciences. And I think I've taken the idea of my title, Man and the World, from Descartes' idea and also from Gromov, because he has a machine, theoretical machine he calls ergo brain, and this replaces the je pense donc je suis. He wants to replace, to go deeper into the expression of Descartes, je pense donc je suis. And this is connected with connection of what we have in mind, mathematics and the world and what we can do with it. The strong involvement of mathematics in recent industrial and technological development is certainly one of the reasons of the renewal of discussion on this topic. The last 20 years have seen a real explosion of high-level technology involving various aspects of mathematics, big data, machine learning, signal processing. These changes are reflected in the recent nomination at institutions of highest level. You can just see what the people who are nominated at Collège de France, at IAS in Princeton, etc. So if you look, I have looked at recent international congresses and round tables and discussion, and some people are anxious, some people say this is beautiful, the next century might be the century of mathematics, but also some say that it might be the century of mathematics, but not of mathematicians. This is one of the anxious questions that was raised by Gromov and Manin and others, because it seems that we need a lot of people able to apply mathematics at the highest level to concrete situation where there is no theory. So we need people of a high level that would not be closed in their office and do pure mathematics without being worried about application. Just to quote Gromov, to make progress one needs radical theoretical ideas as well as new ways of doing mathematics with computers and closer collaboration with scientists. As a symbolic conclusion to my presence with Arnold's homage and here, and a tribute to the richness of mathematics, its never finishing, never ending ability to rethink and recreate starting from itself, and as a tribute to the late Vladimir Voyevodsky, who died in September recently. There will be some events in his honor, I think in a few days. I refer, that's the connection with my topic, to the grandiose program in mathematics which he initiated in response to a demand issued from a crucial application. In the years 2000, Vladimir and some co-authors discovered there was a mistake in a proof of a key lemma in one of their key articles, the key article of Voyevodsky, published 10 years earlier. So this led him to think about the use of computers in proof verification. If this starts like this, you publish an article in the Annals of Mathematics, and it takes 10 years for some people, yourself by the way, to realize that there was a key lemma which was incomplete. It led him to think of the future of mathematics. What will happen? For example, you have other signs that people send a paper for referee to a journal, and it takes 3 years for the referee to read it because it's too long, too difficult. This led him to the new foundation of mathematics, to a program for a new foundation of mathematics, using the old idea of Bertrand Russell, whom we saw at the beginning, type theory, instead of set theory. So this was really a grandiose program where you just stop with set theory and you replace by type theory. The Grand Vision program was called HOTT, H-O-T-T, homotopy type of type theory, to advance the mathematical theory of dependent type theory to the level where it can be used for rigorous study of the complex type theories that are in use today and of the even more complex one that will appear in the future. This whole program constitutes, from a practical point of view, a new global vision of the crucial question of pure and applied mathematics, and also from a philosophical point of view, it's a way to questioning the question, because it's really a mixture of application and theory by itself. So of course this program will take probably many years, but I will finish with this optimistic point of view. Thank you.